Assalamualaikum warahmatullahi wabarakatuh. My name is Syafiqah Binti Abdul Ghani and my partner
Izzah binti Rohaidar
are going to present MAT652 Attribute Structure Group Assignment. We are going to present two theorem, finitely generated Abelian groups and subgroups, and this video presentation is prepared for Mr. Muhammad Asti bin Ma'asar.
Okay, we start with introduction. First, subset and subgroup. For definition, if a subset H of a group G is closed under the binary operation of G, and if H with the induced operation from G is itself a group, then H is a subgroup of G. Thus, integer number under addition is a subgroup but not equal to real number under addition. But positive rational number under multiplication is not a subgroup of real number under addition, even though as sets positive rational number subset of real number. Next definition, if G is a group, then the subgroup consisting of G itself is the improper subgroup of G. All other subgroups are proper subgroup. Then subgroup E is the trivial subgroup of G. All other subgroups are non-trivial. For example, positive rational number under multiplication is a proper subgroup of positive real number under multiplication. It will become a subgroup if it satisfies three conditions. The subset of H of a group G is a subgroup of G if and only if, first, H is closed under binary operation, second, the identity element of G is in H, and last, for all A in H, A inverse also in H. Next is Abelian groups. A group is Abelian if its binary operation is commutative. For example, the family additive properties of integers, rational, real, and complex numbers under addition are Abelian groups. Second example, the family multiplicative properties of rational, real, and complex numbers show that the sets rational and real of positive number and the set rational, real, and complex of non-zero number under multiplication are Abelian group. Beside the set of all real-valued functions with domain real number under function addition is an abelian group.
Finitely generated abelian groups. Every group of prime order was isomorphic to integer modulo p, where p was a prime number. The group integer modulo m times n is isomorphic and cyclic to integer modulo m times integer modulo n if and only if GCD Mn is 1. Every finite abelian group is isomorphic to a direct product of cyclic groups of prime power order. In other words, every finite abelian group is isomorphic to a group of the type integer modulo p1 to the power of alpha 1 times until integer modulo pn to the power of alpha n, where pn is prime number, not necessarily distinct. First, let's look at a slight generalization of finite abelian groups. Assuming that G is a group and that set Gi is a set of its elements, I is in some in that set I, not necessarily finite. The subgroup of G generated by the Gi's is the smallest subgroup of G, containing all of the Gi's. If this subgroup of G is in fact all of G, then the set Gi such that I is in the element of I generates G. In this case, it is said that the Gi's are the generators of G. G is finitely generated if there is a finite set Gi such that I is in the element of I that generates G. Theorem 1. If M divides the order of a finite group G, then G has a subgroup of order M. By Theorem 9.12, primary factor version of the fundamental theorem of finitely generated abelian groups state that every finitely generated abelian group G is isomorphic to a direct product of a cyclic groups in the form integer modulo p1 to the power of r1 times integer modulo p2 to the power of r2 times anti-integer modulo pn to the power of rn, and so on, where the pi are primes not necessarily distinct and the ri are positive integers. The direct product is unique except for possible rearrangement of the factors, that is, the number Betti number of G of factors integer is unique and the prime powers pi to the power of ri are unique. Therefore, by using Theorem 9.12, we can think of G as being integer modulo p1 to the power of r1 times integer modulo P2 to the power of R2 times anti-integer modulo Pn to the power of Rn, where not all primes Pi need to be distinct. Since P1 to the power of R1 times P2 to the power of R2 times anti-Pn to the power of Rn is the order of G, then M must be of the form P1 to the power of S1 times P2 to the power of S2 times anti-Pn to the power of Sn, where Si is between 0 to Ri. By theorem 6.15, Pi to the power of Ri minus Si generates a cyclic subgroup of integer modulo Pi to the power of Ri of order equal to the quotient of Pi to the power of Ri by the GCD of Pi to the power of Ri and Pi to the power of Ri minus Si. But the GCD of Pi to the power of Ri and Pi to the power of Ri minus Si is Pi to the power of Ri minus Si. Thus, Pi to the power of Ri minus Si generates a cyclic subgroup of integer modulo Pi to the power of Ri of order Pi to the power of Ri divides Pi to the power of Ri minus Si equals to Pi to the power of Si. Recalling that the cyclic subgroup generated by A, we see that the cyclic subgroup P1 to the power of R1 minus S1 times with the cyclic subgroup of P2 to the power of R2 minus S2 times until the cyclic subgroup Pn to the power of Rn minus Sn is the required subgroup of order M. For example 1, how many abelian groups up to isomorphism are there of order 360? The solution is by using the long division. The result is as follows, where we will get 1 as the divisor. Thus, we interpret 360 as a product of prime powers, where we will get 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 1. Then, by using theorem 9.12, fundamental theorem of finitely generated abelian groups, we get the possibilities as below. Thus, there are 6 different abelian groups up to isomorphism of order 360. Next is example 2. Find all abelian groups up to isomorphism of order 720. The solution is by using the long division. The result is as follows, where we will get 1 as the divisor. Thus, we express 720 as a product of prime powers, where we will get 2 to the power of 4 times 3 to the power of 2 times 5 to the power of 1. Then, by using theorem 9.12, fundamental theorem of finitely generated abelian groups, we get the possibilities as below. Thus, there are 10 different abelian groups up to isomorphism of order 720.
Theorem 2 proposition. If H is a subset of an abelian group consisting the identity together with all elements of G of order 2, then H is a subgroup of G. Proof of theorem 2. So in this case, we must prove that H is a subgroup of G. So we must to satisfy 3 conditions, which are H is not empty set. For every pair of element AB in H, the product of AB also in H. Then the subset is closed under inverse. Proof of 1. Let AB be elements in H. To show that AB is in H, AB multiply AB equal to E. H is a subset of G, so H holds the property of the group operating of G. Proof of 2. AB multiply AB equal to A multiply BA multiply B. Since G is abelian, AB multiply AB equal to A multiply BA multiply B equal to A multiply AB equal to B equal to AA times BB. Since A and B are elements of H, the order of each is 2 except identity 1. AA equal to BB equal to E. AB times AB equal to EE equal to E. Since AB multiplied by AB is identity, it has order at most 2, either identity or an element of order 2. So AB is an element of H. Proof of 3. Consider an element A of H. If A equal to E, then A inverse equal to E. So A inverse is in H. Otherwise, since the order of A is 2, AA equal to E, thus A inverse equal to A, an element of H. This concludes our proof. Example 1. The set of all elements of order 2 with the identity is a subgroup of an abelian group. Let G be an abelian group and H equal to X in G, X squared equal to E. We must prove that H is a subgroup of G. Proof of 1. Suppose G is abelian. Note that E squared equal to E equal to E. So E in H, and so H is not empty set. Proof of 2. Now take any AB in H. This means A squared equal to E, B squared equal to E. Note that AB squared equal to AB multiplied AB equal to AA multiplied BB equal to A squared B squared equal to EE equal to E. Hence AB in H. Since AB multiplied by AB is identity, it has order at most 2, either identity or an element of order 2. Therefore, AB is an element of H. Proof of 3. Now take any A in H. This means A squared equal to E. Note A power of negative 1 square equal to A power of negative 2 equal to A square inverse equal to E power of negative 1 equal to E. So A inverse in H. Therefore, H is a subgroup of G. Example 2. Let G be an abelian group and let H consist of those elements of G which have finite order. Prove that H is a subgroup of G. Proof, since H is a subset of G, it already has the additivity property. Also, the identity has order 1. So, E in H. Therefore, we just need to show it is closed under multiplication and has inverse. Let xy in H. Let determinant of x equal to n and determinant of y equal to m for nm in integer number. Since G is abelian, xy power of nm equal to x power of nm times y power of nm. But x power of nm equal to x power of n times m equal to em, and y power of nm equal to x power of m times n equal to en. So xy to the power of nm equal to e. Thus, the order of xy is at most nm, so xy in H. Therefore, H is closed under multiplication. Let x in H with determinant of x equal to n, then x power of n equal to e. So multiplying both sides by x power of negative n, we get e equal to x power of negative n equal to x power of negative 1 times n. So the order of x inverse is at most n. In fact, it is n since we can reverse the rules of x and x inverse. So therefore, x inverse in H, and we have shown that H is a subgroup of G.